Hi, this is Yunkai Zhang from UC Berkeley. Today I will talk about my project at Meta, guiding generative recommenders with structured human priors via multi-head decoding. The industry is now moving towards generative recommenders. It formulates recommendation as sequential task. For example, a user has viewed 100 items in the past. Then each item becomes an input token to the transformer backbone. To get the item candidates, we either take the last output embedding to retrieve the similar items, or generate the tokens directly. We can divide the generative recommenders roughly into two categories based on how they tokenize the items. On the left, we have ID-based, where we use one-hot encodings to represent each item. A notable example here is Meta's HSTU. On the right, we have semantic-based, where the item embeddings come from the semantic information of the item, such as the item title and description. For example, in the HLM paper from ByteDance, they used an LLM to turn the item information into a dense vector. The goal of this project is to come up with a backbone-agnostic framework to improve the generative recommenders. We knew from historical, real-world experience that certain business rules are absolutely critical for driving engagement. For example, rules that enforce diversity, exploration, and long-term user engagement. As we transitioned to generative recommenders, our core objective became clear. How do we modernize our architecture to learn those complex behaviors natively without losing decades of proven product knowledge? The bitter lesson by Richard Sutton has been very popular recently. The idea that simple, unsupervised methods that scale with compute will always eventually be systems built based on human encoded knowledge. And the core of that lesson is absolutely correct. Our methods must be simple and scalable. We don't want a model that's patched together with a bunch of engineering hacks. However, recommendations is a unique domain. Unlike other fields, we have decades of high quality, market validated business rules. Discarding all of that expertise to rely purely on unsupervised scaling is a massive waste of knowledge and compute. For example, Meta has some internal item taxonomy, and we can use that to enforce recommendation diversity. Or for high-value events, we should put higher weights on actions like user purchase compared to actions like user view. This led to our final problem formulation of this project. How do we build a unified, scalable framework that systematically integrates this proven business knowledge directly into the end-to-end training of our foundation models? So we started by using a single generative backbone to process users' entire interaction history. This outputs a standard dense representation, which we call as H big T. But instead of making predictions directly from H big T, we take inspiration from LLM's multi-head decoding strategies in the Medusa paper. We attach multiple lightweight adapter heads to represent the different categories in the chosen prior. As you can see in the projection formula, we pass H big T through a learned weight matrix with a silo activation, and add it back as a residual connection to generate specialized queries. For instance, the short-term head is masked so that I only train to predict items 1 through 5, ignoring items 6 through 10. A better example might be the categorical priors. The sports head is trained to predict the sport videos in items 1 through 10. That forces each head to completely specialize in its designated task. In other words, we're doing compatibility masking here. We explicitly restrict each head so that I only retrieve items that are compatible with the signed prior. Eventually, we're able to accommodate a wide range of different priors, as shown in the table here. I want to highlight here that our proposed approach is not just something that looks good on papers. From an applied perspective, this approach provides native safety and controllability. By disentangling user intent along human understandable axes, we give the power back to the product teams. If a trust and safety issue arises, We don't have to guess how a black box model will react. We can dynamically turn off a specific head in production without retraining the core model. And I also think that this makes the whole ecosystem better for both the users and the content creators. For users, the extra interpretability gives users more control. The users can tune the weights across different heads to get more items that are familiar, exploratory, broadly popular, or likely to drive a meaningful action, all depending on their mood or intent for that day. For creators, the same decomposition makes distribution more understandable. They can see which audiences, categories, or engagement pathways are really carrying their content, and serves and therefore make better decisions about the content strategy instead of optimizing blindly for the raw clicks. In real-world scenarios, we really only just have one prior. We usually want to combine them. For example, modeling a user's short-term interest within a specific graph prior. To handle these interacting priors without suffering from data sparsity issues when we have rare combinations, we designed a hierarchical tree structure composition strategy. As you can see in the diagram here, we put the temporal prior at depth 1 and the graph prior at depth 2. This enforces a coarse to fine specialization process. Mathematically, this can be thought of as a recursive process, as shown in the formula here. We share the embedding at the previous level for all its childs. This will encourage information sharing and act as a strong form of structural regularization, which prevents the model from overfitting when it encounters a rare combination of priors. Finally, we can take a look at how we train and serve this architecture. For loss, we use either next token prediction or contrastive learning. But the most important trick here is in group negative sampling. We compute the softmax. We force the head to discriminate only among the items within its own prior group. By doing this, we naturally expose the model to harder, semantically similar negatives, which leads to much better representation learning. We also apply frequency balancing to prevent common categories from dominating the loss, and temporal discounting to prioritize near future predictions. During online serving, since each item gets a score from every head, how do we combine them? We keep it computationally simple. We use the max fusion strategy here. For any target candidate item, we simply take the maximum score from all the eligible heads. This allows the most confident specialist head to dictate the final ranking. Also, for a quick note on future work, we can also explore moving beyond the max fusion to weighted fusion, where we explicitly give higher weights to high-value business events like purchases. And also confidence scoring, using inverse variance weighting to dynamically aggregate the scores. We train the model up to 4 billion parameters across 64 GPUs. Because the heads compute are independent at the same depth level, they are perfectly parallelizable. Each prior head only adds a tiny 0.14% parameter overhead to the model. This system is also highly pragmatic for production deployment. Meta's full internal taxonomy has 3 tiers, and top 2 tiers are very stable over the years. To guarantee long-term system stability, we can design the architecture to only use those top 2 tiers as our priors. Let's now look at the results. We compared our approach not just against the standard backbones without human priors, but also against the state-of-the-art multi-interest networks like ComIRAC and REMI, as well as disentangled representation models like UVAE. These baselines typically attempt to capture diverse user intents through entirely unsupervised discovery. We evaluate on 3 datasets from different domains: video, e-commerce, and news. What we found is that the unsupervised baselines are often less stable, as you can see in the table here. The addition of different types of human priors significantly outperforms both the standard backbones and the multi-interest baselines across both recall and NDCG. The main takeaway here is that using explicit, market-validated human priors as a form of weak supervision is far more effective at guiding the model to learn disentangled representations than relying on unsupervised signals. In addition to the standard recall and ECG, we show that our approach can improve other metrics, such as higher recommendation diversity or helping users to discover new interests. We also show that how it scales with model size and context length. For the sake of time, I will just highlight one experiment here, which is representation space visualization to show why our approach works. Here is a particular user on Pixel AM. That user has 50 past views and 10 target items, and each model recommends 50 items. We use UMAP to visualize the learned item representation spaces across the three models. The baseline HSTU without any priors, the HSTU without proposed item prior, and the HSTU with the multi-interest design REMI. More specifically, the 50 items in the item history are shown using blue dots. The 10 target items are shown using red axes, and the recommended items are shown using squares. In the left plot, the recommended items all tend to cluster in a small region in the representation space, failing to cover some of the target items. In the middle plot, the items recommended by different heads are shown using squares of different colors. We see that the recommended items better covers the target items. Lastly, in the right plot, the multi-interest network recommends more items from the bottom left, while the majority of the target items are actually sitting in the top right corner. This suggests that leveraging existing human priors achieves a more effective alignment between its diverse heads and the user's multifaceted interests, compared to learning the multiple interests in a unsupervised manner like we did in REMI. To conclude, I will take a step back to share my broader philosophy in this space. Scaling laws are incredibly powerful. But relying purely on unsupervised learning before we reach the true AGI is a massive waste of existing knowledge. In recommender systems, decades of market-validated human priors are a strategic advantage. We shouldn't throw them away, and we shouldn't rely on brittle post-hoc patches. We need to integrate them into the end-to-end training. More importantly, as we previously discussed, this approach provides native safety, interpretability, and controllability for our business, as well as the community, which includes both the users and the content creators. Looking forward, I envision an expert-guided architecture. We can keep the humans in the loop to prune the hierarchy, ensuring our foundation model compute exactly the combinations that drive the most value for business. Thank you, and let me know if you have any questions.